Good day, everyone, and you are welcome back to class. We are happy to see you again, and we are glad to know you are following us and you are learning from our channel. Thank for coming back again. We wish that the Lord will continue to grant you understanding, even as you come and learn from our channel. Thank you very much for coming. Let's quickly take our confession before we see what we have for us today. Raise your hand and repeat after me. My memory is blessed by the Lord. My understanding is enhanced by the Spirit of the Lord. My assimilation is accelerated by the Holy Ghost. And I excel in my studies. Alright, let's quickly see what we have today. Today we are taking linear expansivity. In one of our previous videos, we talked about expansion in solid, and we've been able to see how that solid used to expand when it is exposed to heat. And so today we want to see what linear expansivity is, and equally see some calculations that have to do with linear expansivity. All right, so we said linear expansion occur in solid because of the rigidity and the intermolecular force of attraction of the solid, because of the intermolecular force that exists in the solid. So that is why it makes it easy for a particular solid, when exposed to heat, to expand. So solid have a tendency of expanding when it is exposed to heat. Why? Because of its rigidity and because of its intermolecular force. So these are the things that contribute to the fact that these are the things that contribute to the ability of a solid to expand when exposed to heat. Alright, now we said different solid expand by different amounts when heated over the same temperature range. And what we are saying here is that different solid have different level of exposure to heat at which they expand. Now when you expose two solids at a particular degree of heat or temperature, you will see that the rate at which one will expand will be more than the other. Why? Because the rate of expansion are not usually the same. Okay, now we now said, by definition, linear expansion of a substance is defined as the increase in length per unit length per degree rising temperature. So what are we saying in essence is that linear expansivity of a substance is defined as the increase in length. What was the initial length? And when exposed to heat, what is the additional length? That is what we are talking about. The increase in length per unit of the degree rise in temperature. So what is the increase in length? And we want to consider the ratio of the degree of the increase in length to the temperature rise. So that is what we are saying here, and this is the formula L2 minus L1 all over L1 into theta 2 minus theta 1. L2 of course is the length of the new length of the solid. Then L1 is the initial length. L1 is the initial length. Theta 2 is the new temperature. Then theta 1 is the initial temperature. So to put everything together, L1, L2 and minus L1 is E. That's it. We said E. That's the expansion increase. Then theta 2 and theta 1 becomes theta. So this is the formula to calculate linear expansivity. This is the formula to calculate linear expansivity. Now let's quickly take some examples under linear expansivity. Number one example is a copper rod whose length at 30 degrees centigrade is 10.0 meter heated to this. Now when you look at the question, of course you remember our formula that we wrote the other time. Alpha is L2 minus L1 over L1 into L2 minus theta 2 minus theta 1 equal to E, which is, we said L2 minus L1 is E. We let L2 to be increased in the length, then theta 2 minus theta 1 to be theta. Then this is L1. Okay, so now from here now, of course we know we can have alpha equal to L2 minus L1 over L1 theta 2 minus theta 1, right? Okay, so let's try to make theta 2 subject of the formula, because that's what we have to find. Find the new length, that's theta 2. Okay, so let's try to make new length, which is L2, subject of the formula. We know this will be over 1, then by cross multiplication we are going to have alpha. This will multiply this, this will multiply this, this multiply this, this multiply this. So alpha into L1 into theta 2 minus theta 1, close the bracket, equal to L2 minus L1. Don't forget we are looking for L2. And we said that theta 2 minus theta 1 equal to theta. If we still remember. Hope we still remember. Okay. Since theta 2 minus theta 1 equal to theta, then our alpha now will be L1 into L1, this minus theta 2 and theta 1 will now be theta, equal to what? L2 minus L1. Do you understand? Okay, because we are looking for L2, we bring this one. So alpha now will give us L1. So L2 will give us alpha into L1 theta plus L1. So let's expand this. We have L2 will give us alpha L1 theta plus L1. So we can now factorize. So L2 is alpha, L2 now will be what? L1 into alpha theta plus L1. So this L2. I said plus L1 plus 1. Because L1 is already out. So what's common between? We say factorize. L1 and L1 is common. So we write it out. So L theta L1, I said alpha L1 theta divided by L1. Look at it. Alpha L1 theta divided by L1. L1 can cancel L1. Then we have alpha theta. Then same thing, L1 divided by L1. You have 1. So that's how we got our L2. Good. Now if this is our L2, then we can now bring out our parameters from the question. A couple's length is at, this is theta 1. Theta 1 is 30 degrees Celsius. And this is the L1, is 10 meter. Okay? Is heated to theta 2 is heated to 50 degrees Celsius. So we have to find L2. Now, from here we can now slot it in. This is our formula. So let's slot what we have into this. Now, this is theta 1. We've reached it L1, then this. Never forget our formula. L1 alpha theta plus 1. Don't forget, what's theta? This is theta. Hope we did not forget. So theta is equal to theta 2 minus theta 1. So that will be what? What's theta 2? Our theta 2 is 50. What's theta 1? 30. So now theta is what? 20 degree Celsius. I hope you understand that. So this is our theta. So now let's slot it in. We said L2 equal to this. So let's slot this into this and slot in what we have. Okay. So we are told that L1 is what? L1 is 10. Alpha, we are given alpha here to be 0.00000017. Then times what's theta now? 20 plus 1. Alright. I hope you understand. This alpha, this is it we are given here. Theta is what we calculated. Theta 2 minus theta 1. Then minus 1. So first let's multiply this and this. We are going to have 10 into this multiplied by this 0.000017 multiplied by 20 is going to give us 0.00034. Now you have plus 1. This multiplied by this will give us this. Alright. So add 1, then you have 10 into 1.00034. So by the time you use 10 to multiply this, you have 10.0034 meter. So this is the increase. This is the L2, the new length. This is the new length. I hope you understand. Alright, let's quickly take second example. A metal of length 15.01 meter is heated until its temperature rise to 60 degrees Celsius. If the new length is 15.05 meter, calculate its linear expansitivity. Don't forget our formula for linear expansitivity. We said is alpha equal to L2 minus L1 over L1 theta. Okay, so let's quickly figure out. We have to calculate alpha anyway. So our L2 now, what's the new length? That's 15.05 meter. What's the initial length? First length L1 is 15.01 meter. Then the temperature increase is 60 degrees Celsius. You can see this now. I'm not giving to temperature, just have only the temperature rise. The temperature increment is this. So that's it. So let's quickly slot this into our formula and get our answer. 15.05 minus 15.01 over L1. 15.01 times theta 60. Alright, what's going to be our answer? This will give us 0.04 over this times this. 15.01 times 60. 15.01 times 60 is going to give us 900.6. By the time you use subtract this from this, we have this 50.05 minus 50.01, you have 0.04. 15.01 multiplied by 60, you have 900.6. Then by the time you use 0.04 to divide 900, our alpha is going to give, which is linear expansivity, going to give us 0.000044 per Kelvin.